Okay, so this is the last lecture on the support vector machine. SVM. And then we're gonna finish off our discussion on the margin theory. And then if time allows, we're gonna look at a few exercise problems at the end of the chapter. Okay, so I think, many of you, we go through the generalization bound many times, but for some of you, maybe you got used to it and you can see the patterns of what's really going on. But maybe some others might get completely confused. Maybe you can follow the minor details in each step of the derivation, but maybe you may not be able to actually see the big picture about what's really going on. So here are just some maybe high-level remark. About generalization bound. From the perspective of, kind of formulating what to prove and then actually carrying out the proof. So what's the high level? So the first question is, what kind of things we really want to prove whenever we kind of analyze a machine learning algorithm from the perspective of this generalization bound. Typically, what we want to prove is a uniform bound. So we want to show, really there are lots of quantification, but they are all really same for any problem. So all the universal quantification. Okay. Let me just show. Okay, now it should be okay. So all the quantification are really same for any problem. So really the kind of bound we want to show is any problems, whatever we do, so for any problem and whatever we do, we can get a bound. Means we can get a certain bounds with high probability. So that's what the generalization bound is telling us. So there are lots of quantification in the beginning is for any task. So they are the quantification over D and so on. And then the other one is, then the conclusion say that with a high probability, and for any hypothesis, there is a relationship between what we care about the hypothesis, H, and then some quantity that we can estimate. So some of the quantity we can estimate from sample, and some other quantity, they are related to the complexity of the hypothesis set. And there are often some other extra bit. They are coming from, what we really mean about this high probability. So there's just some extra term that's related to high probability. And the high probability is often quantified by probability at least 1 over delta. So there are terms that involve delta here. Okay? Because this notion of a high probability is relative, and there has to be something that's related to this guarantee that we want to achieve. But now, suppose we want to, so this is why we are doing this. The reason we are doing this is we don't really know how the algorithm will behave. Algorithm will find some hypothesis H, depending on the sample S. So we don't know how it's going to behave. Some approach is we really look at the algorithms and try to analyze its property. So that's one approach. Another approach is saying whatever algorithm produce, okay, if we mean, whatever algorithm produced, so in other words, for any hypothesis H, there are some guaranteed property that's true. And then we can now look at the outcome of the algorithm and compute what we get on the right-hand side. And based on the right-hand side, we can make a conclusion on the quality of the algorithm. In other words, having this universal quantification allows us to have an algorithm that can search for an hypothesis and still make a conclusion about it. Now, suppose we want to design an algorithm that not just search for an hypothesis, but something else. Okay, so it essentially does a search, and that search may be over some of these hypotheses set in terms, as we saw in the model selection part. Also, just like this SVM part, maybe the algorithm might try to maximize the margin. So in some sense, it search for, or it optimize some quantity that's a random quantity, because it's strange that there are some noises keep coming in. So maybe it's a problem with Zoom. So there are some quantity that comes from hypothesis set that optimize that gets optimized by the algorithm, but the outcome of the optimization may depend on the sample. So in other words, what's gonna get optimized, so the outcome of the optimization will be random because it depends on S. So we suppose we still want to analyze such an algorithm. So then, I mean, it's not very easy, but one way to do it is saying, so whatever the algorithm optimized, such as the margin that happens in the SVM, if we have the generalization bound that's also uniform about this margin. So in the SVM case, we have. So then if you have such a generalization bound, then this statement can be exploited to make a conclusion about the outcome of the algorithm. So algorithm will compute appropriate hypothesis and also find appropriate margin. But because that statement is uniform, it get applied. It say that with high probability for any hypothesis, for any row, certain bound is true. So we can exploit, we can use such a bound to make a conclusion about the behavior of the algorithm. Okay. So what I'm really saying, I'm saying that the form of generalization bound has a two part. One is for every, it's a few part. The one part of the form say for any task. And then the second part is telling us, with high probability, certain conclusion is true. And then the third part is often, third part is saying, with high probability, certain thing is true, but that certain thing is gonna be universally quantified for all, essentially the search space that's gonna be exploited or kind of searched for by our algorithm. So in the SVM case, the search space is hypothesis together with a margin. So the statement that we are making, say for anything in the search space, any hypothesis, any margin, we have a certain statement. Okay, so that's the form of the algorithm of the generalization bound, and such a bound can be exploited to analyze the algorithm because, algorithm is nothing but a particular, something that choose particular H and particular row, and since we have a universally quantified statement with high probability, that quantified statement can be instantiated for the particular H and row that's searched, that can be found by the algorithm. So any task with high probability, essentially for any element in the search space used by the algorithm, we have a certain bound. That's the typical form of generalization bound for an algorithm. And that generalization bound is used generalization bound is used to analyze the algorithm. Now, that's the kind of one big picture about the form of the generalization bound. And then the other thing is now the question becomes how we can prove this. And then the idea of the proof is essentially there are a few small number of ingredients. The one ingredient is using uniform bound. to handle this universal quantification. Because I mean, we have a universally quantified thing, and we want to have a probability for that everything HM, everything rho satisfies certain property. And then that's handled by the uniform bound. So that's one key technique. The other key technique is we had uses a concentration inequality. Concentrate. Such as Hofding's inequality and so on. But the third one, so they are led us to take care of uniform bound and yeah, so these two will help us to get a bound, but we will end up with some complexity measure, and that on the hypothesis set. So that's really coming from this part, and the last component is some is an upper bound. On the complexity measure. Okay. So, right. So the one way to understand the proof is you can see where, I mean, how the proof uses this uniform bound idea. I mean, the uniform bound is nothing but probability of event A or B is bounded by probability of A plus probability of B. So this is what we are using. So you can, if you see where, I mean, how the uniform bound is used, and then like what are the device that led us to derive the uniform bound, that's one way to understand what's going on in the proof. And the other big component is try to see that how, if we end up with a complexity measure, how we can simplify the complexity measure, maybe by using some VC dimension, or maybe using some bound on the norms of, say, slopes of the linear functions and so on. That's some high overview. So that's what we're gonna do for the margin theory. So last time, we proved something about the, I mean, some generalization bound. Okay, so the bound that what we proved is called Theorem 5.8. Just give you a reminder. So what we proved is Theorem 5.8. And that theorem says the following. For any, so this is really saying for any problem. So this universally quantified, the number of samples also talk about for any problem, and then for any level of probability, I mean, probability that we care about, that we want to achieve, following is true. So Theorem 5.8 in the textbook talk about two things, but let me just mention only one, which involve Rademacher complexity. Say that you get a sample M. So here, F is a set of function from input to the real number. Okay. So I said it's mathematically we are only considering measurable functions. So for every function F, then we can construct hypothesis from the function f by combining with sign, and then compute its risk. So use with respect to this probability, the distribution D. So this is the average number of errors that the function, sign composed with f we're gonna make. It's gonna be bounded by we said this is empirical row margin loss, but maybe the better terminology is empirical row margin risk of function f plus 2 over rho R of m, Rademacher complexity of f, and quantity that's related to the delta. And that was 1 minus delta, at least. Okay. So what that means is with high probability, so it's theorem say with high probability, the risk for every f, the risk of hypothesis generated by f is going to be bounded by the empirical row margin risk together with the complexity of Rademacher complexity of f, and with some extra term related to probability. But one important bit about this formulation is the role played by this margin row. I think it should be row. So role played by margin row. So if the row is large, so then large row, so then this term becomes small, but this term will become large. Okay. And then just a reminder about what this empirical row margin risk or row margin loss is. It's defined by the average through m, and we wrote as f of xi, yi, but this is and this what this means is that it's going to be 0 if they are of the same sign, but if it's greater than rho, that's going to be 0, and it's going to be 1 if they are different sign. But otherwise, so that's in between these two cases, is going to be 1 minus fxi yi divided by rho. So that's the So that's the definition of the composition here. Okay. And if the rho becomes large, then this entire quantity, this entire quantity will get increased because, this case will happen more often, so then the error will get increased. So large rho means the empirical error part is going to be large. On the other hand, model complexity part will get reduced. And rho is small, then the opposite things will happen. And this is called the margin theory because we are bounding what we ultimately care about. So that's this risk part in terms of some quantity that involves rho. Okay. And I said that when the proof is of these theorems uses some result on Rademacher complexity that we looked at before, together with essentially the bound, kind of taking the something smaller, using the definition and transforming the Rademacher complexity bound that we saw before. And the one more ingredient was there was something called Talagrand lemma, which relates the Rademacher complexity of two different hypotheses. So, but this is this going to be enough? And actually, it's not. So what I want to do is that add something here. So reminder together with. Let me just write it here. So why it's not enough? And the one reason is now what we want to do is to reason about the behavior of the algorithm, and we don't really know what kind of margin the algorithm will compute. Okay, and then what algorithm? So this rho corresponds to the margin of the algorithm. This rho corresponds to the margin of the algorithm, but this margin will be computed by the algorithm depending on the sample S. So rho is not going to be deterministic. It's going to be random. And we want to reason about the algorithm. So what we want, so we need to modify these bounds in three ways to reason about, or to get some idea about the behavior of SVM. Support vector machine algorithm. I mean, for the non-separable case. So what should we do? And then there are three things that need to change. First, we need to make it uniform. With respect to rho. Okay. What that means is that we want to somehow change the bound and then insert. This means is inserting here. Essentially, we want to insert something like universally quantified rho. Okay. Maybe rho is bounded. It means instead of 0 to infinity, we want to bound it to 0 to r. But essentially, we want this kind of things to be added. That's one thing that we have to do. So that's one change we need to do. What's going to be the second change? Second is that we want to replace Rm of f by something else, something simpler. Because Rademacher complexity depending, I mean, it's good. It's an accurate measure of the complexity, but it's hard to deal with and get a sense about what's really going on. So we want to replace this, the Rademacher complexity of R of f to something simpler. So that's related to this part. And then the third one is relatively simple. That okay, we have this empirical low margin loss of f, but that's not quite the same as the empirical loss in some sense computed by our algorithm. So empirical loss computed by our algorithm looks like this. So okay, let me just write it down. So this one can also be written in this way. Minimum of 1, maximum of 0, and 1 minus. Okay. So 1/n summation 1/n 1i WXI. Okay. So we are thinking about some simple function defined by the inner product. So that's what we did the definition. But in the what's being used by the SVM doesn't really have this minimum. Okay. So I mean it's different, but so the what's closer to SVM is that it doesn't have this minimum. In SVM. As I said, the other part, so this part is related to the slack variable in SVM. Psi I. So in the non-separable case, it optimizes the square norm of the weights, the square norm of the W plus C times sum of the slack variables. But the right-hand side is related to the slack variable. But it's empirical row margin risk or empirical row margin loss involves some extra term minimum. So we want to get rid of this. And that's not going to be, that's quite easy because if you get rid of this minimum, things become larger. Okay. So anyhow, these are three things are what we need to do to get something, let's say, to get a generalization bound, let's say something more direct to the SVM algorithm. So that's what we're gonna do. So first, we'll carry out we'll change this theorem 5.8 so that we can talk about, it can also make the statement uniformly about the row. So that's our next results. So here's so bounds. It's not exactly SVM, but something closer to SVM. So what's the result here? The result say theorem 5.9. Theorem says can have a usual universal quantity for distribution. And M natural number. Delta. And there are some bounds called, I use R here. So you say that probability, with high probability, certain bound will be true. What the bound is but uniform with respect to our hypothesis set F. So this F is just some set of functions from input to the real number. But then there is another, the universal quantification of row margin, which is between greater than 0 but smaller than or equal to R. Then we meant to make a statement which bounds the risk of hypothesis generated from F with the row margin loss, well, empirical row margin risk. So F. But now we're gonna have some extra term. So beforehand, the previous theorem have a rho over 2 Rademacher complexity of F, but it's gonna become, so 2 will be changed into 4. It's different color, 4 here. So maybe use different color here. That's because of the universal quantification of a rho. And then there will be some extra term that's related to the universal quantification of a rho. So this means we're gonna have to use, as I said, union bound. And then this extra term will allows us to manage this union bound. And that one is going to be log of 2 to R M. Then the remaining bit is similar to the one that we already have, and but the numbers are a little bit different. 2m log so delta, but the number that we put at the top over delta is, instead of 1, it's going to be 2. And that's should be high probability. So that's the statements, and the actual statement in the textbook have something about, instead of Rademacher complexity here, something that also uses empirical Rademacher complexity, but the proof and the arguments are essentially the same. So we're gonna look at this theorem. So you can see that, I mean, our goal is to have a universal quantification of rho. So we want to have a statement that's true for all rows with high probability. Then we have to pay the price. The price is some constant went up. So it became 2 became 4, 1 became 2, and we have some extra terms. But these are the price we pay to get a universal quantification of a rho. So really, the universal quantification of rho is handled by the union bound. And then all these other extra, the increase in the bound are there to deal with this. The application enables us to use the union bound idea successfully. Now the question is how we can prove this. So for the proof, we make some particular, instead of proving this directly, we prove something slightly different. So we consider, because they're universally quantified for, if you think about what kind of, how many rows are possible, there are uncountably many. So we first find some way to reduce this uncountably many rows into countably many rows. Because uncountably many rows, you cannot really express it in terms of summation. You cannot really sum over uncountably many stuff. But if there are countably many, you can use a summation and then do some reasoning about it. So we are thinking about the row K. They are in 0 to R. But this is any countable sequence of rows. And also we are thinking about any countable sequence of epsilons. Okay. So then, and actually what we're gonna do is we will, I think there will be the epsilon, there will be something delta, which are closely related. They are epsilon k is fixed, delta k will be fixed, and vice versa. 0 and So it's just positive number. Okay. So I mean, the epsilon and the delta will be mutually defined. I'm using delta here because that will make it clear how the previous theorem is used in this case. Okay, so now if we apply the theorem 5.8 that I explained in the previous slide, we can get the following for K. Probability that for F the risk. That's right, is essentially the same thing. Okay. It's 1 over delta K. So this is, I changed the direction. I moved this from the right-hand side to the left-hand side and changed the direction of this inequality. So now it's, instead of less than equal, it's a greater than. So then that will change the probability as well, because I mean, less than case, we have probabilities greater than 1 minus delta. So then this whole thing will be bounded by above by delta. Okay. So that's the outcome of the statement before. But then this universally quantified statements can equivalently express in terms of supremum. So really, universal quantification is really about inequality involving supremum. So we can erase this part, replace that part, and say, so if you take a supremum or F here, that's if the supremum is larger than the one on the right-hand side, there will be, so our estimate, what we really care about is larger than the what we estimated by a large margin for some F is going to be bounded by delta K. Okay. That's the outcome, the direct consequence of theorem 5.8. And then we're going to rewrite this term as an epsilon K. So that's why I said the epsilon K and the delta K are closely related. And if you do so, and you just write down equality and then express this in the relationship between delta K and epsilon K in terms of delta K equal blah, and this delta K will become epsilon K squared to n minus exponentiation. That's what we're going to get. So why we are doing this? So the reason we do this is because now we want to add. So if you have a, this is a for, if you can see, the K is outside and we want to put K inside. So we want to have a uniform bound for all K. Okay. So then here's what we do. So we choose epsilon K to be some epsilon plus 2 K divided by M. And then we write the things. So instead of supremum, we now want to take a supremum over F as well as K. Then because we are taking the supremum, everything related to k have to move on the left-hand side of this inequality. So we have r of sine f minus k f 2 to the rm minus epsilon k and greater than 0. So that's the probability we want to bound. So it's a some. So what's this probability say? It's a probability that some f and some k behave badly. For some f and some k, the real quantity that we care about is larger than the bound that we are trying to impose. Okay, so something bad happens, and that we want to bound that probability of that something bad happens. And then we use uniform bounds. So probability that something bad happened for some f and k, that's going to be bounded by probability that so one of the things is this thing is holds f, and essentially the same thing here, greater than 0. We have this bound, and the reason is, if the supremum is larger than greater than 0, there will be some k for which this supremum on the top will become larger than 0. So that this big disjunction is going to be true. So this means just logical implication, and this is true. And then if you now do the union bound, that's going to be bounded by sum over all the probability, where we have a supremum f, and the quantity here is greater than 0. But we showed, the quantity there is going to be bounded by, this one, the exponentiation of minus 2m epsilon k squared. So this whole thing need to be bounded by some k exponentiations of minus 2m epsilon k squared. And this is, if I now plug in the definition of this epsilon k, which is given here, so then same as k. So actually it's not, this is bounded above by the epsilon square plus m over log k. It's just, if you just unpack the definition and use the fact that epsilon is positive and the square root of log k divided by m is also positive, then you can get this bound. Now, if you simplify this bound, what we have is k. So this m gets in one side, we have exponentiation of minus 2m epsilon square. For the other side, m gets cancelled, and then the exponentiation and log just cancel each other, so then we get k squared. This. Now, if you sum all the 1 over k squared from 1 to the infinity, that's going to be, I think, pi squared divided by 6. Right. So this is same as 6 pi squared. And that is bounded, big pi squared divided by 6 is bounded by 2. Get this outcome. So So that's what we can get. And now, where are we? So we have something quite close to the final statement that we want to get. Yeah. So the final statement is over this guy. So we get something quite close to this, but instead of universal quantification for all rows between 0 and R, we have something universal quantification only over K. Okay. So that's the statements. So we said this is greater than, and that's a statement that we proved. I mean, we're gonna rewrite this epsilon this form in terms so that it can be expressed in terms of delta, but that's a statement that we get. Now we have to replace this K by the quantification over all rows. Okay, so how should we do it? I wish I have some way to copy it. All right, so here's some other trick of the proof. The trick is now, so what's our goal? We want to replace supremum of K to supremum over rho in 0 and 1. So that's what we want to do. And so here's an idea. The idea is we pick rho K to be R divided by 2 to the K. So we make a particular choice of rho K that's based on this. So if you make this particular choice, then say rho 0 is equal to R. So then here are just some immediate things that we can find. I mean, because this, if you increase K, this rho K gets smaller and smaller for every row. We can always find, so for every row, we can always find rho K that's smaller than rho, and rho K minus 1 that's maybe equal or larger than rho. Okay, so rho, so for any K, any rho. So this is something that we can find. But now if we find something like this, then there are a few statements we can make. I mean, what we know, one thing we know is that rho K minus 1 is equal to 2 times. Yeah, so 2 times rho K. Slightly, this is better. So okay. Then another thing we know is that the rho is smaller than or equal to K minus 1. So by combining this, we can say 1 over rho is bounded below. So 1 over rho divided by 1 over rho K minus 1. And right, so then let me just this way, make it a bit easier. So 2 over rho is divided like this, and that is the same as 1 over rho K. And that's one thing we can get. So that's one observation. The second observation is now if you take for K, take is equal to log of, we divide R with rho K, because rho K is this defined like this. we divide r by rho k and take a logarithm with 2, that's exactly the same as k. So one thing that we can talk about is for quantity rho over k is going to be square root of rho of k. It's going to be bounded same as square root of rho of 2 rho k. But yeah, this is larger than because of this relationship. I mean, this is larger, bounded above by rho of 2, and so it's 2r divided by 4. So here are two facts that we collected. And we have a quantity like this. Now we now use these facts for, let me kind of rephrase. So what we proved in the previous right. So what we proved is this. Just we take back the previous slide. Is this a statement, which is the probability of primum for k sine minus rho k to r in f minus epsilon k greater than 0. That is bounded. If some bad thing happens, it's going to bound it by rho. So the statement of the theorem said opposite of this, which is a good thing happens with high probability, 1 minus delta probability, at least 1 minus delta probability. Now if we, for epsilon k, its definition was epsilon k was epsilon plus square root of m rho k. Okay, that was the definition of epsilon k. And now if you do simplifications, that's the same as putting a minus here. And now what we're gonna do? So we will just replace. So what if the probability of this is delta? So if we replace this whole thing, not include. So this from the primum. So if we replace this is primum, which is, we say, the greater than 0 by something smaller. So then if we replace by something smaller, then this probability will also be bounded by delta, okay? Because something smaller, so then its probability will be bounded. I mean, probability that this something smaller going to greater than 0 will be also bounded by the delta, because I mean something smaller implies the one something larger. I mean, it's smaller than equal to If something smaller is greater than 0, that implies something larger will, of course, greater than 0. And so the bound above will imply the probability will be bounded by delta. So then using the facts that I highlighted on the top, so we're going to replace the yellow, the underlined part with something smaller. And that is, we're going to write here. Just premium over F and rho are sine of F minus this is RK as rho of F and 2 times rho 2. Step 2, we have 4 times F. It's epsilon minus rho 2. So that's what we're gonna do. So we will replace the yellow part with the red part. And I'm claiming that that is smaller. That is because whatever row we pick, so whatever row we pick here, we can find row K that satisfies this inequality. So then if we replace the, the 2 over row, I made some mistake. So we can find the row K with this inequality. So what this means? This means that this means that the 4 divided by row will be larger than 2 divided by row K. Okay, so if we subtract something larger, then of course the quantity will become smaller. Similarly, we know that the log of K here for that specific row K is going to be, by the inequality that we proved here, is going to be smaller than the quantity that I wrote over there. So the quantity that I wrote will become, that if you subtract something larger, then that will make things a bit smaller as well. Finally, for row K, I didn't quite write it here. Row K is smaller than rho, and if you replace the above, rho K by something larger, then this empirical error will get increased. So rho margin risk or rho margin loss will get increased. So what this means, for any rho, we can find appropriate K such that the quantity on the top will be something larger than or equal to the quantity on the below. So any rho, we can find something in some sense larger. So then if you take a supremum of all the large elements, that will give us something larger than supremum that will take something smaller elements. Okay, so that implies this inequality is true. So that's why the probability that this supremum is greater than 0 will also be bounded by delta. So that's how you can prove this statement. And now this thing is expressed in terms of, I think this is I mean, that's exactly the form that we want to prove. So just coming back, what we proved this statement, say for F and rho, the risk that we will, okay. So the risk, sorry about this. Yeah, so the risk is going to be bounded by the rho margin risk of F and 4 times the quantity, the Rademacher complexity, and then some extra term that's really coming from the union bound of rho, and some quantity related to delta with high probability. Now, the next thing we want to do is to replace this Rademacher complexity part. Right. So here's the next result. Which is theorem 5.10. And the theorem say if we have a sequence of x's, so this is sequence of inputs such that input is bound sequence of size m, but all the inputs are bounded by r. So this r is different from the r that I used before. Okay. So it's bounded by r. And also assume the function set is all the linear functions. But the weights or the slope that we are using is bounded, its norm is bounded by lambda. If that is the case, then its empirical Rademacher complexity, we can bound it by using the bound for the input and bound for the slope of functions in F. What's the condition? It's r squared. So it's really saying if inputs are not very large, and then the slopes are not very large, and we can use that information to bound. I mean, slopes are not large, inputs are not large, then the Rademacher complexity is also not very large. So the proof is actually quite simple in this case. Statements. Yeah. So if you say for x is x1 to xm, so then we just calculate this empirical Rademacher complexity is going to be 1 over m expectation over all the uniform variable Rademacher variable over m, such that we take a supremum over all the functions in f, but the functions are determined by this slope, bounded slope, and sum of I is equal to 1 through m Rademacher variable times this function w xi. And what's nice about linear function is, so now what I'm going to do, so what's nice about linear function is that we can move the function is linear, so we can move sum together with the sigma I into the other side. So if we do so, we get we just directly manipulate here. So if we do so, you can move this whole thing. and becomes some m sigma. But then we are at that point we are using so-called Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality say that if you take inner products to any two things, that's going to be bound, and then its size is going to be bound by norm of x and norm of y. Here we are thinking about the two norms. So then if we apply the Cauchy-Schwarz, we get this supremum of w, and then the other part is summation of I is equal to 1 sigma I xi. And initially, this supremum is over both multiplication, but the right-hand side doesn't depending on W at all. So we can reorganize the supremum. So we can move supremum inside. Then supremums are now moved in like this. So then if you take a supremum, then this whole part can be made to equal to lambda. So and then if we can take out lambda, then that's going to give us this. So lambda divided by n sigma arrow sigma I xi. And typically, I mean, at this point, you might feel that it's quite difficult to do anything further. But one thing you can do is that you can view this the term inside the expectation as follows. So you can view this as the square root and then take a square root. But now notice that the function square root x is concave. So we can use the Jensen's inequality. If you take expectations of over multiple inputs, then that's smaller than the expectations. I mean, so yeah, let's just use the Jensen's inequality. That means if you move expectation inside, then that will give us something larger. And sigma I square this. Now what's good about this is if you take two norms and then it's a square it, then you can kind of express what's going on algebraically. So this whole thing is the same as summation I and j and so m sigma I, sigma j, xi, and xj. But because sigma I, sigma j, they are independent, and then their average is 0. So if I and j are different, yeah, and okay, if I and j are different, if we take okay, let me just write it here. Same as m. Because of linearity, we can move out to m expectation of j xi straight half. And sigma I and sigma j are different, then they're independent and the average is 0, so they all disappears. The only term that survives is the case where I and j are the same. So that's the same as sigma I 1 to m sigma I square xi half. but this sigma I square is always equal to 1. xi is a norm of xi, and then this norm of xi is bounded by r. So the whole summation is going to be bounded by m times r. Yeah, I mean r. This norm square is bound by r square. It's bound by m times r square. So if you do the calculation, that becomes same as the lambda square r square. That's exactly the form that we want to prove. So now I have about 2 minutes, so then I can finish off. Yeah. So this is the bound that we got, but now if we make an assumption and said, so if you make an assumption on D and say, well, any sample in D, its element is going to be bounded by R prime. Let's call it R prime. So what's our assumption? Assumption is probability, and that's why sample from D that norm is bounded by R prime has a with probability 1. So it's always going to be bounded by R prime. So that's one assumption. So we add this assumption. And also for hypothesis set, so instead of saying any hypothesis set, we assume our hypothesis set F consists of functions that maps. So just linear function where slope is bounded by lambda. If we do so, what can we do? One thing we can do is now we can replace this Rademacher complexity into the bound that we showed you before. We only showed bound for empirical Rademacher complexity, but that implies bound for the Rademacher complexity. So this can be bound by square root of lambda square r prime square divided by m. Okay, so then we are getting in the final form that we have, almost in the final form, except that the only remaining part is this guy, but this one will be bounded above. I mean, this is bounded above by some term that appears in the support, I mean, something in the slack variable or something very close to the slack variable support vector machine. So this is bounded above like 1 over m. So 1 over m, sum of I is 1 to m, and it's a maximum of 0 and 1 minus I. So the maximum of 0 and some term, but what goes inside is 1 minus yi xi divided by 4. So that's, as I said, is close, and this whole thing is closely related to the slack variable psi. Okay, so that gives the final generalization bound that we want to get. So generalization bound said for all hypotheses in our new hypothesis set, they are linear functions with bounded slope. For margin and risk is going to be bounded by this quantity that's being related to the error computed by the support vector machine times 4 over rho with this measures, which is computed from the norm of the upper bound on the norm of the slope, as well as the size of the input, and some extra terms coming from the union bound of rho, and some other terms coming from delta with high probability. Okay. Yeah, so that's it for today, and sorry about going overrun for about 3 minutes. And I'm gonna stay here for about 5 more minutes. So if you have any question, you can ask me. So then next week we'll move on to the part on the kernels. Okay, so thank you very much.